Hey everyone, welcome back to Calculus 3. This is going to be part B of lecture 21. So where we left off, we had just defined the double integral, and we furthermore talked about how to evaluate double integrals, namely how to convert a double integral into an iterated integral. Okay, we've done some examples, and now, we've done some sort of working examples, some slow going examples, trying to kind of set up the idea. And now what we want to do is look at some additional examples. So let's take a look at this one. Okay, so let's take a look at this example. Say we want to evaluate the integral, the double integral of 1 minus 1/2 x squared minus 1/2 y squared dA, right? And so, and keep it. Notice this is actually the this is the example that we started with in the part A of the lecture, right? And we actually use this function alongside a partition of a pretty bulky partition. It only had 16 squares to kind of set up the idea of how this integration would work. But now what we want to do, and we came up with a decent approximation, but now what we want to do is actually calculate the full integral. Okay, so we want to evaluate this. And what's the region? You're always going to need a region. And the region here is where R is the region given by 0 less than or equal to x less than or equal to 1 and 0 less than or equal to y less than or equal to 1, right? So namely, this is that square from 0 to 1. Okay. Okay, and so we can just kind of draw a picture of the region. Sometimes it helps to do that. So you've got your x and you've got your y. And what we're interested in is the region, right, that is defined by this square here. Okay, and so I'm going to set up a delta x vertical across. It's going to sum across the x-axis, and so that's gonna set me up for a dy dx order of integration, right? And so the integral here is pretty straightforward, right? The double integral of this function is going to be equal to the iterated integral from 0 to 1, from 0 to 1 of, then it's going to be, let's see, just the same function, 1 minus 1/2 x squared minus 1/2 y squared, and then it's going to be dy dx. Okay. And this is super easy to integrate, so we can do the inner integral really quickly. This is going to be 1 minus 1/2 x squared times y, so these two would both get a y, and then this one down here becomes y cubed over 6. Okay, and so we need to evaluate that from 0 up to 1, and then integrate a second time with respect to x. Okay, and so that integral is what? Well, everything, you're going to basically plug in 1 for all the y's here, and so what we're going to get is 1 minus 1/2 x squared minus 1/6 dx, and we could simplify that a little further, and we would get 5/6 minus x squared over 2, like so. Okay. And then we have to integrate, do the outer integral, right? So the outer integral is just going to add an x to everything, and so I get 5/6 x minus x cubed over 6. Okay, and that's going to go from 0 up to 1, and so what do I get here? I get 5/6 minus 1/6, and then minus 0 minus 0. And so what do I get? I get 4/6. which is 2/3, right? And that's what we said. If you remember at the onset of part A, we had said that, oh yeah, this integral, we got something like 0.67, but the true volume is 2/3, so 0.66666666 forever. And so here we can see that indeed that is what we can get when we use this double integral approach. Okay, very good. So that's kind of a straightforward example. Let's take a look at another example. And this example is going to be very much more challenging. And it's mostly to kind of make a point, right? So the difficulty, so when we think about regular integrals like what we're used to, something like this, right? An integral that like what we're used to from single variable calculus, the difficulty of this guy, of this definite integral, is pretty much dictated by the function f, right? Here, the difficulty is based on the function f, right? And specifically what I mean by that is, like, it doesn't matter what a and b are, right? The integral is tricky because of f, right? Or it's easy because of f, right? So you calculate the integral and then you evaluate the upper and lower limits, right? And you take the difference and there you got your definite integral. With double integrals, it's a totally different story, right? For double integrals, the difficulty is very significantly influenced by the region. So the difficulty is based on the function f and not the interval. That's what we have in single variable calculus, right, with an integral like this. But for double integrals, the difficulty is very much influenced by the region, which is like saying, the integral is really easy if a is 0 and b is 1, but it's really hard if a is 1 and b is 2. That makes zero sense in the case of an integral like this, a single integral, but in a double integral scenario, that's actually the case. Like, it can be the whole problem can change based on the region that you're interested in. And so the problem we want to do next really exemplifies this. So here I'll write the problem out and then we'll talk about it for a second here. So find the volume of the solid region bounded by the paraboloid, and the paraboloid has got this equation: z equals 4 minus x squared minus 2y squared. Okay, so it's going to be find the volume of the solid region bounded by this paraboloid and the xy plane. Okay, and so if you look at this expression, I mean, we've done a couple of examples already that have polynomial, equations like this, like equations of, something plus x squared plus something y squared. I mean, so just simple polynomial, and they didn't present, like the previous example, for example, that one didn't present any real difficulty. But this one is going to be a lot more difficult, and specifically because of the region that's being selected here. Okay, and so I'm going to draw the picture. This is going to be a really bad picture, but I'm going to try to draw the picture just so we can get a sense for what we're up to here. Right, just so we can get a sense for the what this guy might look like. So it's a paraboloid, and it kind of looks like this. It sort of comes, well, let me try to draw the xy plane first. So we'll say this is the xy plane, right? Here's x, here's your y-axis, and the paraboloid kind of lives above the x-axis, or above the xy plane, like so. It's actually not too bad. It kind of looks like this. Okay, now remember there's no tilt here. This is supposed to be totally symmetrical when it intersects the xy plane. Oh, sorry, that's the y-axis. Okay, so it actually intersects up here at -2 on the x-axis and at +2 on the positive x-axis. And then these intersections are not nice numbers, so they fall somewhere between positive and -1 on the y-axis. Okay, so that's kind of what it looks like. And so this region in the xy plane is an ellipse, right? So the base of the paraboloid in the xy plane is an ellipse. Okay, and it's going to specifically have the equation x squared plus 2y squared equals 4. So that's what this ellipse is. Okay, and so the way we're going to set this up is we're going to use a dy dx orientation. Okay, so we're going to do it this way. So this is going to be like a delta x here. Okay, and so that'll make our outer region go from -2 to +2. So the constant bounds are -2 less than or equal to x less than or equal to 2. Okay, and so what about the variable bounds? Well, so the variable bounds are what makes this problem so tricky. The variable bounds, so if you start with your ellipse, your equation here, x squared plus 2y squared equals 4, if you start with that, then you can quickly figure out that y squared is equal to 4 minus x squared over 2, and so y is equal to plus or minus the square root of 4 minus x squared over 2, right? And so what that means is that your y is going to vary between these two endpoints. And so those are the values that you see here and here. Those are the edges. And so you're going to have, on one end, you'll have negative square root of 4 minus x squared over 2. That's going to be your lower bound. And your upper bound would be the positive version, 4 minus x squared over 2 square root. Okay, and so these are going to be the limits of the integration for your inner integral, and this is going to be the limits of integration for your outer integral. Okay, and so now all we have to do is set it up and do it. So let's go ahead and write this guy out. So the volume, right, is going to be equal to this, -2 to +2. And then that's your outer integral. And your inner integral is going to be negative, and then 4 minus x squared over 2, and then 4 minus x squared over 2 at the top. And then the function is just the given function, 4 minus x squared minus 2y squared dy dx. All right, so obviously the polynomial is not the problem here. The problem is the variable bounds on the inner integral, right? And so that's going to be the tricky part here. Okay, so let's go ahead and work this out. I'm going to give myself lots of space on the next page for that. And what do we have? Well, so we're going to integrate that, and the integral is easy to calculate. It's the bounds that are hard to evaluate. And so when I calculate the integral, it's going to be 4 minus x squared times y minus 2/3 y cubed. Okay, and then that needs to go from negative square root of 4 minus x squared over 2 up to 4 minus x squared over 2 square root. Okay, and so when we plug, so we got to plug all this in and deal with this. That's the tricky part of this problem. Right, now, if you were to choose a different region, this would not be, you'd not necessarily have the same issue. Okay, so let's go ahead and do this, and I'll just go through it. But if you feel like it, you could skip ahead, 15 or so minutes, because this is going to be kind of a lengthy one, but it's an interesting one. It's going to test your algebra. So we've got to evaluate the expression at the top, and then subtract off of that the evaluation of the expression at the bottom, right? So when we do that, we get something like this. Right, so we plug in 4 minus x squared over 2 square root. Okay, and that's the evaluation at the top, right? So this again is your y cubed. You got to plug this in for y. Okay, and then we have to do the same thing at the bottom. And so we get 4 minus x squared times negative square root of 4 minus x squared over the square root of 2 minus 2/3 times negative square root of 4 minus x squared over square root of 2 cubed. Okay. And now it's just an algebraic, kind of a sorting out of all this algebra, right? It's actually not terribly tricky. It's just cumbersome. All right, so kind of looking at this first part, you can bring the 4 minus x squareds all together. And so what do you have there? You have 4 minus x squared to the 3/2 power over the square root of 2. And over here you're going to get, so then you'll get minus 2 times 4 minus x squared to the 3/2 power over 3 times the square root of 2. So your denominators are a little off. Oh, actually, this should be 3 times 2 to the 3/2, right? So you actually have square root of 2 cubed. So be careful of that. I made that mistake. Okay, and then it's going to be minus, and then you got to do the same thing for this other piece, except you've got a few additional negatives to deal with here. And so this would be negative 4 minus x squared to the 3/2 over the square root of 2. And then this is going to be plus 2 times 4 minus x squared to the 3/2 over 3 times 2 to the 3/2. Okay, let's just go through that one more time and clean up a few things that I should have done. Let's namely get rid of the brackets. So I got 4 minus x squared to the 3/2 over the square root of 2 minus 2 times 4 minus x squared to the 3/2 over 3 times 2 to the 3/2. Okay, and then what I'm going to do is I got minus, so I'm just going to make that a plus, and so then it's 4 minus x squared to the 3/2 over the square root of 2, and then this one will be a minus. So minus 2 times 4 minus x squared to the 3/2 over 3 times 2 to the 3/2. Okay, all of that's the new integrand. Now we have to obviously simplify this before we attempt to integrate it. And so let's combine these. We can combine these two, the first and third term and the second and fourth term. And so when we do that, it's relatively straightforward. They're both the same, so it's just 2 times it, and then over the square root of 2, and then minus 4 times this other one. Okay, so you got this guy now. All right, now what we'd like to do is combine this whole thing together, and we can do that if we can make these denominators the same. And how could we make the denominators the same? Well, we would have to multiply this one by 2 and 3, right? So this is going to be 3 times 2 times square root of 2. So 2 times the square root of 2 is 2 to the 3/2 power. And so what we need to do is do the same thing over here. And so we can do that. So we'll go 3 times 2 times square root of 2. And so we have to do 3 times 2 up top, and then we have the other 2 there, and then we have that thing. And I'm just kind of writing it out like this just to make sure that everybody's following. If I just start plugging in numbers, people will definitely lose it. Well, not everybody would necessarily, but so that's what you have there. And so what is this? This is 12. So 12 times 4 minus x squared to the 3/2 power over 6 times the square root of 2. And then minus 4 times 4 minus x squared to the 3/2 power. And then this is going to be the same thing. This will be 6 square root of 2 as well. Okay. And so now we can combine them. All right, so we can combine them now. And well, maybe I'll do it over here. So 12 minus 4 is 8, basically, right? That's all you have to do there. Like so. And let's pull all of the constant terms out. And so this will be 4 over 3 times the square root of 2. Then the integral is negative 2 to 2. And then it's just going to be 4 minus x squared to the 3/2 power. Okay, dx. There we go. So that's kind of as good as it gets for the inner integral for right now. And this, so what do we? How do we now move to the outer integral? Right. Now what we want to do is evaluate the outer integral. So this integrand here, if you recall, can be accomplished by using trig substitution. Okay, and so we can use trig substitution, and this is from like Calc 2 to do this one. All right, and so basically you could set up a right triangle, and what you'd find is that x should be equal to 2 sine of theta, and that's going to mean dx is equal to 2 cos theta d theta. Okay. All right, and so kind of keeping that in mind, we're going to work on this integral. Okay, and so what we can do is let's rewrite it here. It's 4 over 3 square root of 2 times the integral negative 2 to 2, and then it's 4 minus x squared to the 3/2 power dx. All right, and we're going to rewrite this as a trig integral, and the way we're going to do it is using this substitution that we just laid out, right? And so this would be equal to 4 over 3 times the square root of 2. Now the integral bounds will change, and I think, again, you can kind of work that out, but it's going to be, notice this is symmetric, negative 2 to positive 2, so it's negative pi over 2 to pi over 2, and I'll just let you kind of, you can figure that out on the side. That's not the hard part by any means. But then instead of 4 minus x squared, we're going to have 4 minus, and then it's going to be 2 sine theta squared. So that becomes 4 sine squared theta, right? And that's raised to the 3/2 power. Now remember, dx was equal to 2 cos theta d theta, right? So you're going to have 2 cos theta and then d theta, right? So that's the total substitution that you need to do to get this outer integral, right? And now it's just kind of a lot of trig tricks. Well, it's just a lot. Yeah, well, it's some trig tricks. So let's factor out a 4, and then we'll have to cube it and then take the root. And so what do we get here? We get 4 divided by 3 square root of 2, and negative pi over 2 to pi over 2. And factoring the 4 out, so it'll be 4 cubed, and then take the square root of that. And so all in, you're going to get a 16 there. And then what you're left with is 1 minus sine squared theta. Okay, and that's actually to the 3/2 power still. And then you're going to have the 2 cos theta down here still. Okay, no problems yet. This 1 minus sine squared theta, that's just cos squared theta. That's the Pythagorean identity, right? So we can use that. Let's see, the 4 times 16 here, that's going to be 64, so I'm going to pull that out. Okay, and then this is going to be cos squared theta to the 3/2 power times oops, I think I pulled the 2 out here as well, and so that'll be times cos theta. Okay, yeah, good. No problems. Okay, and let's see. So then, what can we do next? So this is cos squared to the 3/2 power. So that's like cosine squared theta, the square root of that to the 3rd power. So we can basically, the square here and this denominator would kind of undo one another. So we get 64 over 3 square root of 2 negative pi over 2 up to pi over 2, that integral. And then this is just going to be cos cubed theta. And then that's cos theta, and then d theta. And so finally, I think we get it down into this nice form that we can actually deal with. Of cos to the 4th theta. Okay, and then again from from Calc 2, if you look at trig integrals, you will find that this one can be integrated, right? You can integrate this, and this cosine to the 4th power theta, and what you end up with is 60. On the outside, you still have the constants that you've been bringing along the whole time, but this cosine theta all raised to the 4th power, this is going to be equal to 12 theta plus 8 sine of 2 theta plus sine of 4 theta all over 32. And that needs to be evaluated from negative pi over 2 to positive pi over 2. Okay. All right. And so that last stretch is tedious, but not too bad. So we'll start with the upper bound, and so what you get here is 12 pi over 2. And then notice that everything else is sine, and because you got 2 theta and 4 theta, you're basically evaluating multiples of pi, right? And so sine is 0 at all of those multiples of pi, and so this would be plus 0 plus 0. Oh, sorry, there's a 1 over 32 first. I pull that out. Okay. All right, so that's the upper bound, and then minus 1 over 32, and then you evaluate the lower bound. Oh, I'm so sorry. I left something out here. Well, that's okay. We can do it this way. So minus 1 over 32. No, you know what? I need to go back. I apologize. I think I must have left something out here. Yes, I did. I wanted to do this differently. Sorry. Just 1 second. Let me just back up. This will literally take 1 more minute. So this guy here, I want to use the symmetry argument. So cosine is basically, so because we're integrating from negative pi over 2 up to pi over 2, we can actually cut this in half and do 0 to pi over 2 twice, and you get the same result, wouldn't you? Right? And so what I want to do here is I want to change this to 128 over 3 square root of 2. So that's just multiplying this all by 2, multiplying the whole integral by 2, and then I want to integrate from 0 up to pi over 2. Okay, and we can do that because this is a symmetric integral. Okay, namely yeah, if you look closely at this, you will see that it's if you just plot this function, you can see that pretty quickly. It just kind of makes it a little bit quicker. It's also a nice review of a lot of the things from calculus too. So anyway, so then this is what I said before. I kind of skipped over that step. Okay, and so this should be 12. I mean, nothing changed in the integrand, so it's just the constant out front and the bounds. So plus 12 theta plus 8 sine of 2 theta plus sine of 4 theta all over 32. And that's from 0 up to pi over 2 now. Okay, it just kind of makes it the simplification a little easier if you do it this way. Okay, and so now we can easily plug in those bounds. right? So we'll do the top bound first, and so this is going to be 1 over 32 times, so 12 times pi over 2 gives you 12 pi over 2, and then we had said that, oh, this is sine of pi and this is sine of 2 pi, so those are both 0, so plus 0 plus 0, and that's the upper limit. We can do the same thing for the lower limit, and there we can see everything is 0, 0, 0, 0, they're all 0. Okay, just for the people paying attention who are kind of new or are a little rustier with this. All right, so it looks like this. All right, so this is all 0, those two are 0, so it's really just these three constants that need to be multiplied together and figure out what they're worth. So 128 over 3 times the square root of 2 times 12 pi over 64. Okay. And so you can simplify this down and you'll get 24 pi. First thing you can do is see you'll get 24 pi over 3 times the square root of 2. Right, that's just canceling those two and multiplying everything together. And then you can simplify this down to 8 pi over the square root of 2. And then we can rationalize the denominator and we get 8 pi times the square root of 2 over the square root of 2 times the square root of 2. So you get 4 pi times the square root of 2. That's probably about as good as it gets. That is as good as it gets, yeah, definitely. And so that is the that is the volume of the region that is that we described at the onset, so 2 pages ago and 20 minutes ago. Right, so this region here, right? So you've got this paraboloid here kind of coming out of the xy plane. We just want to know the volume of that thing, right? And we found that the volume is based on this base, which is an ellipse, which has this equation, right? And what made this problem tricky is not the constant bounds of the outer integral, but the variable bounds of the inner integral had these really nasty upper and lower bounds. So when we plug all of that in, we had to go through a ton of algebra to sort it all out. We're finally able to reduce it to this expression here, and the outer integral is also like not a totally straightforward one. We had to use trig substitution on that. And so all in, when we get down to the end, we do get this nice precise result for that volume. Okay, but this one really helps to illustrate how even if the function is easy to integrate, the double integral may be very challenging to evaluate due to the bounds, right? Due to the region of interest. Okay. All right. I think we'll end it there. So those are some good examples. And then next time we will take a break for a second on the multiple integrals and look at change of variables and polar coordinates, which we will need for some of our additional applications that we're going to develop. So we'll leave it there, and we'll see you all. We'll see you all next time. Take care.